Hi, this is Andrew. Thanks for joining me. Today we'll be talking about Spanning Tree Protocol, which is STP. First, I'll talk about why it's needed and what it does, and then I'll do a demonstration about how it works using Packet Tracer 519 from Network Academy. So, let's get started with a picture. Right here, you see we have two switches, and those two switches are connected, and you don't see the full wire, but the orange wire goes to port 1 on both, and the blue wire goes to port 2 on the both, and these beige wires go to, theoretically, devices. Now, if you look at it, you see lights aren't on, the switches aren't actually turned on. I just didn't bother turning them on. But we have the picture here. Now, if you look at this, you might think that you have orange going to orange, blue going to blue, so that doubles things up. That's what we're going to get to later in the next chapter, the next video with Ether channel. This video assumes that it's a standard configuration, standard setup, and these are separate wires, and the switches see them as separate wires. So what happens here is, in a normal situation, this device plugged into port 14 right here will send the switch something. It'll send a frame to the switch, and the frame has a destination address, and that destination address will be some MAC address. The switch will look in its table and say, that's plugged into port 12, and it'll just send it out on port 12. Sometimes, or frequently, it will send a broadcast frame, and that frame reaches a switch, and the switch looks at the broadcast frame with a MAC address of all Fs, and it sends it out on every port except the one it came in on. So port 14, that device sends a broadcast, and it goes out to all of these ports. Now, what happens here? Port 14 sends a broadcast. Without spanning tree, what happens is it will send to, or we'll call it switch 2, will send that broadcast to all of these devices. And then it goes up to switch 1 on both wires. And switch 1 receives the broadcast from blue, and it says, okay, I need to send this out on all the wires. And it sends it back to orange. And it receives it on orange and says, okay, I need to send it out, and it sends it back to blue. Now switch 2 receives that broadcast, and it says, okay, I just received this broadcast, I need to send it out on blue, and then it receives it on blue, and I need to send it out on orange. Comes up here, and you can see as I'm drawing, you can't keep track of what's happening, but the broadcast goes in an endless loop because there is a loop. Now, it could be that this blue wire is connected directly to this between switch 1 and 2, or it could be that theoretically this blue wire could be going to another switch in the closet or in another location, and this switch, and this is trying to create redundancy so you don't have a failure if that switch goes down. But we're looking at it just from the perspective of two switches plugged in. Now we have a loop, and that loop, whenever you have a broadcast, that broadcast will go forever. And you might wonder, why does the broadcast not reach its time to live and expire? Frames don't have a time to live. Packets do. From an IP perspective, they have a time to live, so the routers will stop forwarding them at some point. But if we want to look at a frame, this is a diagram of a frame. We have preamble, destination MAC address, source MAC address, ether type, and then the data, and that's where the packet is. And the switch never looks at that, it just forwards everything that's there. All we have are the destination and source MAC addresses. So they will go on forever. And it'll just keep forwarding that frame, and that frame never degrades because each time it reaches a switch, the switch reads it, recreates it, and sends it back out. It'll just continue on and on. Okay, big deal, one frame, that's not a problem. But let's say that this device sends out a frame every second, and this one every second, and this one every second. you can see that the number of frames going on the network will increase, and it'll just keep increasing. And at some point, the network resources will be completely used up by forwarding these bad frames. So what do we do about it? Well, from a spanning tree perspective, all we have to do is say, we're going to shut this port down. And there is a process of figuring out which port in the loop to shut down. We can do that one. We're just going to shut down one. We don't even need to shut down this side because that link goes down just from that one switch, from that one port. So now, imagine that broadcast comes in on port 14. It goes out to these devices. It goes to 11. It goes to orange on 1. And then that comes out and the broadcast goes out on all of these ports on this switch. And it can't send it back on the blue because this end of the blue is blocked. That's a blocking state. Now, you could shut the port down. You can go into this switch and just do a shutdown command on that one port, and that's one way to do it, and that'll stop your loop. But the problem there is, what happens if the orange cable fails? And it's not just a single cable. This could be going to another device. Well, in that case, you want the blue to come up automatically. And that's what Spanning Tree will do. It will make the blue cable come up automatically. You don't have to worry about manually going in and running a command to bring your network back. The orange cable goes down, then the blue cable comes up, and this one is broken somewhere or there's something wrong with it. So it is a straightforward process to come back up. It's a process that does not require any user intervention. So that is Spanning Tree, and it involves any kind of loop. And frequently the diagram will have 3 or 4 switches, any kind of switching loop. Sometimes it might be a situation where there are multiple loops going on and there's a whole process. Spanning Tree is a very old concept and has been in place for a long time. It has been updated to do things that are more modern. And they can be things as simple as making it happen faster. So this goes down, instead of taking 30 seconds, it might be 10 seconds. For that time when things are, when it's figuring out that the switch is not working or that link is not working anymore, and it has to switch the blue cable from disabled to enabled. That process, when that's happening, there's no communication between the switches. So the faster that can happen, the faster the network starts working again. So that's one thing that's been done. The other thing that's been done is you can have separate blocked ports on separate VLANs. And in a sense, that can create a load balancing. So on VLAN 1, you're using the orange cable, and on VLAN 10, you're using the blue cable. There are other more current ways of doing this kind of configuration, and we'll talk about them, primarily Ether channel, in a future video. But this is where we are right now. This is the understanding of Spanning Tree. So now let's look at the actual configuration of it. So here we have a packet tracer that shows the Spanning Tree protocol loop prevention, how it's working and what it does. Now if we look at it, as I said, most of the time you're looking at 3 switches in a Spanning Tree demonstration. In real world you might have 3 or more, but it's pretty rare that you're looking at 2 switches in that situation. So here we have 3 switches, and you can see right behind the label there is an orange dot, and that's saying that that port is blocked. Now on the other side of it, it's green. That's saying that port is not blocked, but obviously without both ports open, it's not going to allow things through. So it really, you can say it's blocked, but it's not fully blocked because it is allowing some communication through. We can look at that, and we will see that in future labs, future lessons. But for now, just recognize that it's partially blocked. So what they have us do is look at the Spanning Tree configuration on each of the switches. Well, actually, we'll do a quick verification of PC1 to PC2. So let's just ping. This is PC1. We're pinging 192.168.1.101. That is PC2. We see we can get there. Now, just based on the diagram, we can see that it would be going from switch 1 to switch 2 to PC2. So now next up, they have us looking at the spanning tree configuration. So we're going to start with switch 1, and I'm going to run the command show spanning tree VLAN 1. So let's get in here, enable show spanning tree VLAN 1. And what we see here is on, let's put it over here, switch 1, we have 2 gigabit ports, and they're both green. One is root, and that's actually the one that's connected to the root bridge, and one is designated, that's the one going in the other direction. So the root is G02, and both of those are forwarding. We're not worried about FA01 that's connected to the end device. So the other thing we see here is the root ID, the root bridge priority ID is the default. And the bridge ID priority on this switch, on switch 1, is exactly the same. But the reason that it shows another switch as the root bridge is because it moves on to the MAC address as the tiebreaker. And that's, in a sense, kind of a random number. There's no value, there's no situation where a lower MAC address is better than a larger MAC address. It's just a way of deciding, and a consistent way of deciding. So we now we're looking at switch 1. Based on this, it tells us that switch 2 is going to be our root bridge. So let's start by looking at 3, because we kind of know what's going on there a little bit. So we go to 3, and we do enable and show spanning tree VLAN 1. And here we have 01 is the root port, and that is forwarding. And then 02 is blocking. That's an alternate. So that is actually blocking. That's where the loop is stopped. So they can still communicate general information about what's going on with the network, but they don't actually send frames. And that prevents the broadcast storm that we talked about. So, and you can see again, they're using default priorities. Now, if you wanted to change that priority and you wanted 3 to be the root bridge, you could do that. You could say 3 is going to be a different priority. Anything lower than 32,768, it takes that priority and adds the 1 there. So you drop it by 1 or 10 or 1,000 or whatever, and now this becomes a root bridge, and your network changes its configuration. So if we made 3 the root bridge, then we would have one of these ports would be disabled. So let's just take a look at 2, and we will see that that matches. Enable show spanning tree VLAN 1. And here we see that the root ID address and this bridge ID address match. It's saying that this is the root bridge, and obviously everything's forwarding there as well. So now the next thing they have us do in this lab is actually breaking this connection here. So what we want to see is we want to just witness it happening. So what we care about is switch 3. You see we're in a blocking state right now. And the other thing we care about, PC1, I'm going to repeat the ping, except I'm going to do -n and 1,000, so it just keeps going. And you should be able to see this happening in real time. So I'm going to click here, and I don't have anything highlighted. I'm going to click on the delete. I'm going to delete that link. So we go back to the PC, and it is timing out. And we run the command here, and we're still in a blocking state. But as we go, that's going to change from blocking to learning. And now and you see there were the status changed. One of the things to keep in mind is this link going down means that the network stops working, but it will come back on its own. It will come back without administrator intervention. You don't have to connect to switch 3 and do a no shutdown command on the port. It's going to come back on its own. It's going to figure out a new way of distributing its connection. And there we go. Now we're forwarding. That turned green, and now you see our ping is working. So that is the process that Spanning Tree follows. And if we want to go beyond what the lab is telling us to do, we can take a network cable, plug it back into gigabit and gigabit, and now you see almost right away we get the orange dot returns because it's trying to figure out what's going on. It gets blocked again, and these are still orange. So if we go back to PC2, you see that things are timing out again. So we plug the cable back in, and it stops working again. The network stops working. You can't get from one side to the other. But just like when we unplugged it, plugging it in gives us time for it to come back. So now it's green, and now our ping is working again. So that's the process of Spanning Tree and how it all works together. That's the process of the convergence of the network and seeing how it works. So that's all I have for you today. Thanks for joining me.